Morning, everyone. Welcome back to the first technical session of the night, routing, MAC, and wireless interface. So the first speaker is Guo Yu. I try my best. He is currently a postdoc at EPFL. His research interest is routing in sensor networks and distributed computing in social networks. He's gonna present the paper, Efficient Graph Planarization in Sensor Networks and Local Routing Algorithms.
Thank you for the introduction. So this work was started when I was at the University of Geneva, and it's joint work with Robert Jarif and Pierre Leon and José Romy. So the purpose of this work is to obtain a routing strategy for sensor networks. So we want to be able to do point-to-point routing. And the classic way to do this is first to compute a planar graph, and then we use this structured graph to route the messages. So a planar graph, a subgraph is just, the objective is just to select some edges. So here, the colored edges, out of all the edges, so the original graph is a gray one, and you want to select edges so you don't have two edges that intersect in this drawing. And then once you have this planar graph, subgraph, you want to find a strategy to route messages from any point to any other point. So this is the objective of this workshop, and I will do it in three parts. First, I explain our planarization technique, and I will describe a routing algorithm dedicated to this planar graph obtained, and then I will briefly show some simulation results. So a lot of work has already been done in this way, like first computing a planar graph and then routing strategy. But the main difference that we have here is that the one of the coordinate system. But just before going in this, I thought what I will focus on is unit gaze graph, which is a commonly used model for sensor network. So two nodes, they will be connected if they are distance less than 1, and they will not be connected if they are greater distance. And so the difference that we have with the previous work on this topic is a coordinate system. Here in this work we use a coordinate system that is called VRAC for virtual row and for coordinates. And the idea is that the node will have as coordinates the distance to some set of anchors. So here we have three anchors, A1, A2, and 3. And each knows the distance to all the three anchors and does not know its Euclidean coordinate. So this is the main difference. And using this coordinate system, we want to do all I explained before. First planarize the graph and then do the routing. So the interest of this coordinate system is that you directly use the distance to the anchor, and you don't compute from them Euclidean coordinates. So you skip the phase that may introduce approximation error, and the idea, the objective is of this coordinate system is to be more robust to error introductions. And because we have this, in this case, 3D coordinate system, we cannot use classical planarization routing techniques. So for our planarization technique, we will need orders. So the free order we define this way. We have a node X, and we say that a node Y, which is in this region, will be bigger than X in the first order. In this region, it will be bigger in the second order, and in this region, it will be bigger in the first order. So these are partial order that we will use in the following. And a result from Matt Schneider from 87 said that if you take a graph where you put an edge between X and the Z that is minimum for each of this order, so you have a graph with, for each node you will add like 3 edges. And this graph, there is a result that says it is planar. The problem that we encounter with this graph is that when you want to compute this minimum, you need to compute it over all the nodes of the graph. So therefore, it's not local planarization technique. And the second drawback is that it does not respect the distance condition of the unit disk graph. So the graph, the planar graph you obtain may not be planar. Still, it's a good basis, and we use this as a starting base. So instead of looking at all the nodes in the graph, so that before it was the minimum of all the nodes, here we look at the minimum only in the neighborhood of x. So Ax asks to all the neighbors to know which one is the minimum for order 1, for order 2, and order 3. And for each order, it selects one z, and we keep these edges. The problem is with this solution, we may still have some intersection, and the condition which is not respected as with the previous construction is depicted in this picture. So you have x here, and you look at the nodes that are bigger for some order here, and the neighborhood is everything that is inside this side curve. So here you see that y is the minimum neighbors of x for this order, but outside the neighborhood of x, you see another node z that is smaller than y. So if you want to apply Schneider technique, you need to keep the edge xz instead of xy. So for this, what we do is we extend our construction to the second neighborhood. So if we do the selection of edges using the second neighborhood, and that we keep the edges whose length are at most 3/4, then our result says that the graph we obtain is planar. So we have an illustration here. We keep all the edges only in the neighborhood, and we can see that we have two intersecting edges. But if we apply this transformation, so we look at the second neighborhood, and we keep only the edges whose length are 3/4, then we obtain this graph. And we see that there is no intersecting edges, so it's correct, it's planar. But the problem is this graph is sparse, and here you have an edge which is quite short, and if you want to route from this node to this node in the planar graph, you have to make all this long way. So the graph obtains planar, but it does not have good properties because you don't have stretch guarantees. So next step is to improve this planar solution. So this is the drawback of this class construction. And to improve this result, we add two new hypotheses. The first hypothesis is that the three anchors that are used to compute the coordinates, they form an equilateral triangle. And the second condition we add is that a node x knows the distance between the anchors. So it knows its distance between the anchor and the distance between two anchors. And then, using this new coordinate system, we slightly modified the three orders. And so now, not y will be bigger than x if it is in this region. So it still looks the same, but if you want the detail of how I will change, you can look at the paper. It's not very important. Just we are able to define this three order correctly. And we still keep the same way of selecting the nodes. So we look in the second neighborhood for the nodes that minimize these three orders, and we keep all pairs. So if the pair xy is actually an edge in this graph, then we keep it. If it's not an edge, so it means the y is in the second neighborhood, but it's not in the neighborhood, then we add what we call a virtual edge, which corresponds to a path of length 2 in the original graph. So this is this situation. So we will put the edge x to z, and this will correspond to the path x, y, z. So this solves the problem that I illustrated before. And what we have with this new graph we obtained is that it is planar. And if you have a path of length L in the original graph, from a node x to another node y, then in the new graph obtained, you have a path whose length is at most twice longer. So you have good distance preservation property. And the other good point of this planarization technique is that you need only very few broadcasts. In fact, you need at most, in the worst case, 6n, so 6 times the number of node broadcasts. So each node will broadcast in average 6 times its ID. And this is the worst case. In general case, you will have 3 times the number of nodes broadcast plus the number of virtual edges. And the number of virtual edges is very scarce, is very small, as this illustrates, this simulation result illustrates. So here we have the average degree in the original graph, in the original Unix graph, and for a network of 300 nodes. And here you have the number of virtual edges that were computed over 1,000 runs. So when you have average degree in virtual graph that is 5, so it means you have 750 edges in the original graph, approximately, then in the output graph you just have a bit more than 1.5 edges in average. And when the average degree increases, the number of virtual edges tends to 0. And so we have, I just showed you a good efficient technique to planarize this graph, and now I will explain how we can use it to perform good routing on this graph. So for this we need what we call greedy region. So this is the same reason as for the order. So a node will be in the greedy region for anchor 3 if it is in this red zone for the node text. And this is greedy region 1 and this is greedy region 2. And why we use this greedy region is because if we have the destination node which is in one greedy region, the node x will simply forward the message to the node that is as neighbor in this greedy region. So it's just greedy routing. And so it will do so until it reaches D, or until it reaches the node that is does not have D in the greedy region. So this is this situation. Now X wants to send the message to D, and D is not anymore in the greedy region. And in this case, what we do is what we call zigzag. So we will send to the node on one side, on the greedy region on one side, and then on the other side. And we will do like this until we reaches a node Z that is in the same region as D. And what our result says is that if we have some connectivity condition, which is basically that a node has a neighbor in each greedy region, then our routing algorithm will guarantee delivery. So why this connectivity condition is interesting is because recently there was a result saying that if you have a triangular partner graph, then there is an embedding that ensures greedy routing to deliver any message. And this result, it can be seen as comment of this result I just cited, because in the result that says that there exists an embedding, you have to compute the coordinate of the nodes. In this result, we start from the embedding and we propose a routing algorithm that uses the real embedding and which also guarantee delivery. So it's some parallel between these two results. And so as I promised now, I will give some quick simulation results. So we compared, so we don't have any good routing algorithm to compare with because of the use of draft coordinates. So the only algorithm with which we could compare in the same setting is a greedy algorithm. So we first compare the success rate, again, depending on the average degree of node in the original graph, and in the square area with 300 sensors. And so we see that when the degree in the underlying graph is small, we have not that good success rates. But this is explained because the connectivity condition we use in the theorem, they are not satisfied. But when we increase the node degree, then the connectivity condition becomes satisfied and the success rate tends to 1. Whereas for the greedy algorithm, we still have success rate that remain below 80%. So our algorithm improves the success rate of greedy algorithms. And concerning the stretch, we measured the path length divided by the distance, the Euclidean distance between the two nodes. So, and we did this experiment introducing some error on the placement of the node. So instead of having its exact distance to the free anchors, it will have the distance to the free anchors plus some percentage error. So that we will, for each node, for each coordinate, we will add some noise chosen at random between 1 and plus and minus 1%, up to plus and minus 5%. And we see that the stretch, so it's the efficiency degrade when we introduce more noise, but still with 5% error, we have a stretch that is less than 2, so which is still not bad. So this way, I presented you an algorithm that efficiently computes planar graph and this in a local way, and a routing algorithm that is dedicated to this planar subgraph. So both results are robust against some noise on the coordinates, but for the routing algorithm to work, we need to have some connectivity condition. So the next step, what we are working on now, is to get rid of this connectivity condition, and for this we try to adapt some greedy phase greedy algorithm to this planar graph and this new coordinate system. But it does not work easily because we don't have this notion of, we don't know when to stop walking around the place. We don't have the same nice condition as when we have Euclidean coordinates. And the other direction we want to study is the influence when the anchors, they are not forming an exact equilateral triangle, but instead they are making some triangles that look like equilaterals. So can we, is it still robust with this kind of error, and what kind of other error we can be robust with? So thank you for attention.
Question from the audience. So congratulations, you have a bulletproof postdoc. Oh, yes.
So you showed how the routing works for the destination being in one of the 3 colored regions. Can you also show how the routing works if it's not in one?
Yes, this one.
Yes.
So
the idea is in the colored region, right?
So you go to one polar region, you start on one side and you go to the other side, and at some point, if the connectivity conditions say that you always have a neighbor in the colored region. So you go from side to side, and at some point it will be too far away. So your neighbor, the last neighbor VK, will have a neighbor in the colored region, but from the point of view of VK, which must be in the non-polar region of X. And this one, this node Z, it has to be closer to D.
What if the destination D is not in this colored region? What if the destination D is in the white region?
If it is on another region, like this. And there is two cases. Either you are in one of these three color regions, this is this case, or you are in one of these three non-colored regions, which is this case. You see the difference?
Yeah, but here D is also in the colored region. The destination is always in the colored region.
Yeah, okay, so maybe in this this slide I put some stripes, but this is not the same region. Like what the gritty, what I call gritty region is this free region.
Okay, let's set the speaker again. Our next paper is Control Strategy, Mobility, and Energy-Aware Routing in Robotic Wireless Sensor Network. And our presenter will be our keynote speaker. So I'm going to skip the bio introduction, because otherwise it will take too long. I'd rather leave the time for Ivan to tell us what's new in his group.
Okay, so it's control, state, mobility, and energy-aware routing robotic sensor networks. So the problem we're looking at is we have fixed source and fixed destination, but long-term traffic like video reporting. But we have also mobile relays like sensor robots or vehicles. And we would like to find a route from source to destination and to move each relay node to an optimal spot to improve the reporting quality, to minimize transmission power and moving distance. So we are combining two things, control node mobility and energy-aware routing. Our proposal will be a hybrid routing mobility framework to optimize the network communication, and also the second part is to provide straight mobility while preserving connectivity during the movement. So, assumption we have a power model which where the cost is proportional to the distance to the power. Each node knows its own location, and they update this through the hello messages. And mobility cost is proportional to distance. We started from research on this paper, Goldenberg, etc., which gave the same problem first solution, but they gave some solution which had mobility in routes. So there are two inefficiencies observed. First is in the routing algorithm itself, they apply greedy which had two long paths, or nearest forward progress which had two short paths, which in both in terms of energy was suboptimal. That's one thing. And the second is they proposed moving a bit, communicating, stopping, communicating, then moving again, then communicating again, then moving. So that moving was in the rounds, which in the round itself we thought maybe is not necessary to do. So these are the drawbacks of existing approach. There are another approach which had some improvement, but still we kept moving around as the solution strategy. So our approach was first to find initial energy efficient path, immediately something which is going to be good at the end. And we applied that for search as the general strategy to discover the path. And even if source and destination are disconnected initially, we still can find solution, and then through mobility they will connect later. Plus we looked at direct mobility, so moving along the straight line from initial to final position while not losing connectivity. Of course that's the criterion, because previous solutions were saying that it's not possible. So our approach is start with effort search to find initial route. If initial route is found, then we can look at move directly from initial to last position. If not, we will still find enough nodes and we will move them to the final position and connect later. So we had before one paper which had some ideas of this, but power optimization we applied was generally not optimally applied. Optimization on one hop at a time, but at the end, number of hops and not the optimal because we did not optimize along the best path. So that was a detail. So we improved here. So the first solution is dynamic optimal progress routing, where we know in advance how many hops are optimal at the end. Then we make a selection locally while routing path, having this in mind, and each time choosing the node that eventually will produce that many hops at the end. So initially not optimal, but at the end, when the routing is created, it will become optimal. That's called dynamic optimal progress routing. It just gives easy formula which node is the best to choose next to progress to our destination. That's metric used in depth first search as the primary metrics. So we have depth first search, which if it finds a route, will give this as the algorithm giving the route if it exists. If not, it will just find enough nodes to later on connect. But the depth first search by itself works in a standard way. So choose the best choice. If it works, go on. If not, go back, try the second best choice. Don't try the choices already tried by somebody else. It's a depth first search strategy, which is embedded into depth first search with this optimal algorithm that I showed at the beginning. So, if source and destination are disconnected, like in this example, then what will happen in our algorithm is it will find, let's say, 3 nodes, and they will be moved to the final location, and then connection is at the end, because there's nothing better if we can create anyway. So that's one scenario that can happen. We can move directly if the initial depth first search is successful to actually reach destination immediately. Then we can start reporting immediately and improve the quality of reporting by moving. And we are looking at the way to move directly straight line from initial position to the final position. So for that we get two basic successful algorithms in the paper. The first one will create initial path from source to destination, and then each node will have different speed to arrive at the same time. So as I demonstrated already, or maybe try again. So the further node has faster speed, so they want to, if they are initially connected, and they choose the speed so to arrive at the same time at the end, then we prove that they are always connected. That's a geometric argument. So they keep connectivity by choosing their speed to arrive at the same time. So there is initially communication only at the beginning to establish who is where, and then there is no talking, it's just moving straight to the end. And that's one. The other thing is, if you want to keep the same speed, so if all robots have to keep the same speed, then it's still possible, but they just have to be closer to each other. So there's a kind of constraint how close they must be at the beginning to keep connectivity while moving at the same speed, so not arriving at the same time, but connectivity is there. So the first one arrives faster than the others, but they keep connected, and at the end they arrive. So there's a second algorithm that keeps connectivity while improving. So experiments, of course, show that what is expected that this dynamic power over progress approach that I showed at the beginning, we choose this optimal number of nodes at the very beginning, so that at the end the power efficiency is best, is proved to be also better than other approaches from existing papers and from our previous paper in several metrics, including the mobility and power. So we improved on all options. So we improved the minimal mobility, improved the transmission power, and we also improved on the mobility itself in one round directly, not with the, so including communication also minimize this one. So in all metrics we managed to improve. we show the feasibility of this and that it works. So in conclusion, we get unified framework for mobility and power awareness, and as I said, we have increased energy savings, guaranteed message delivery, and we also managed to work in disconnected scenarios at the beginning, because then that storage will just discover enough nodes and connect them. And with the direct movement into different scenarios, it keeps connectivity to finally connect along the optimal paths. So that was my presentation. Any questions?
How do you guarantee that all the destination robots that are on a single line? Because I didn't see that when you give an example, shows as all the robots finally will reach to guarantee that those robots that are on a single line.
Yes, so that first search will try to connect also the relation immediately if possible. So there are two options. If it finds, then we show how to move directly from initial to last positions. And so the key trick is only to choose different speeds. So initially they could be in different configurations. You measure the distance, and if you agree when to arrive at the end, you know how much time you need and what speed to choose. And only geometric argument shows that connectivity remains. Destination is initially found by depth of search. We find the initial route. Well, if initially you don't find destination, then okay, maybe I'll show this. Okay. If you initially do not find, then of course. So here, so initially if it is disconnected, the only thing you can do is just move and at the end connect. That's the best that we have. The second part is if you actually connect initially, this is initial part. Then you move to different speed to arrive at the same time. And we prove that it's keep connectivity in the paper. Second option is same speed for each. But they have to be initially closer. Then it doesn't have to be closer. And then by moving the same speed, they don't arrive at the same time, but they keep connected all the time, and at the end it's improved. So that's what we have essentially in the paper. I hope I was a bit clearer.
So what is your metric for maintaining uniform distribution from the source to the destination? What's the metric? Is it just the distance? So you want to have equal distances, or do you want to have equal link qualities?
Two metrics involved. One is we want minimal distance for the movement plus minimum, actually 3 metrics. Minimal communication among robots, which is by the way product, not really measured. Just we stop communicating immediately and just let them do the job. Second is minimize the movement of the robots by asking them to move directly, because that's the optimal. So you are here and you have to move there. You move straight, that's the optimal already. Nothing else. And then at the end, what we want is when they already settled and they have long-term video, that the power for routing is optimal, which means you need optimal distances at the end. But we create these optimal distances at the beginning.
Okay, so it's basically all about distances. I'm curious because the link quality will change in different environments, because maybe there's an engine standing nearby and though you need to shorten the distances.
Of course, if you make it more complicated, more real, you have to change things, you have to anticipate in advance what is going to be environment at the end, maybe you have obstacles, you can make it more complicated, of course. It's just initial attempt to show something nice.
Okay, thank you.
Of course, the more real you are, the more headache you have.
So actually, I have a question.
Yes.
I may miss something. So if I understand it correctly, the reason you want the robot to move to the destination is to save communication energy costs in the long run. So I'm curious because I know once a robot starts to move, it consumes a lot more energy compared to communication. So I'm curious how long the sensor network or the robot network have to communicate to justify the movement.
Well, that's obviously a good question, but here it's a kind of several things done at the same time with a long-term outlook at the end. So we don't have a precise, if we know how long is the video, then the things change. So if the video is shorter, then all this criticism is going to be applied. We assume that it's going to be long-term video. So we want to fix the network at the beginning with short cost, small communication cost, small distance cost, so that we can have a relaxing video at the end for a long time.
Do you have any?
Now the exact metrics you have to improve this. But anyway, this is the kind of, if it is going to be like that, then it's probably the best. Because at the end we go to stable position and then we cannot improve. Okay, so if we have 1 day video, it's the best.
Okay, I'm just wondering whether there's any online like a feedback loop. So if once they move to the destination and things might change, the battery may be low and their communication may
That
change.
can be added, of course. That's if add more things, it can be made more complicated and better actually in practice. But this is just initial attempt. Because what we did, we improved in all metrics that we have seen. So avoid communication, avoid extra mobility, and improve the path at the end. So all this was done. And now you can add extras and make it more real. So, yes, it's a future work that you are suggesting.
Thank you.
It's good. Thank you.
So our next speaker is Vahid Samin Parcho. He's actually a PhD student in UC Irvine, and his research area is Mac protocol design and Mac protocol optimization. He's gonna talk about his work on Bing Mac, a hybrid Mac for ultra compact wireless sensor network, wireless sensor nodes. Excuse me.
Thank you for the introduction. Here's the outline of my talk. So some wireless sensor networks applications require the sensor nodes to be very compact, very small, and lightweight. So for example, in a monitoring application that is used for predicting cerebral palsy in preterm infants, the sensor nodes are smaller than your fingertip. So we cannot have too many features on them. For example, the sensors have a very limited memory, 4 kilobytes for the whole driver and vertical stack and so on. The clock width is very high, they don't have very accurate clocks. Limited battery life. This particular sensor does not have trigger sensing, and we are mostly interested in the star topology single hop networks, and in most of the real world deployments have been single hop. So what we're looking for is a simple hybrid MAC protocol. Unfortunately, the majority of the existing MAC protocols cannot be applied with ultra-compact wireless sensor. For two main reasons. Either the protocols are too complex with a large footprint, or they require tight synchronization, which is hardly impossible to achieve on these tiny sensors. So you can have two options: CSMA, ground dubbing. Of course, CSMA cannot be implemented on these sensors because of the carrier sensing, but since we are developing a MAC protocol that can be used in general, we consider this algorithm, and we compared our algorithm with these two. So the round robin is a reservation-based protocol, but the difference with TDMA is that it does not do clock synchronization, and just the base station sends the query messages and sensors reply with the data. So BinMAX stands for binary medium access control. The term binary comes from its collision resolution mechanism. So it's a receiver-initiated protocol in which the base station sends the query messages and was replied. In this protocol, we put most of the burden on the base station. Since the base station is powerful and usually line power, we can put most of the burden on the base station to keep the sensors as simple as possible. So it's a reservation-based protocol, working in a round-robin style, and there is no scheduling phase involved. And it's analogous to the scheduled contention scheme. So these are the four mechanisms used in DMAC that I'm going to cover one by one. So the distinguishing feature of our contention resolution mechanism is that we do not perform carrier sensing on sensor nodes. And carrier sensing is only performed on the base station during the collision detection. So we employ a scheduled contention mechanism. By that we mean each time slot, instead of having a single node ID, it has a range of node IDs from a minimum ID to a maximum ID, assuming that the sensors have numeric IDs. So we try to keep one active sensor for each time slot. And if there are more than one active sensors, more than transmitters in the same slot, we rate the slot and assign different slots for each active transmitter. So this is how we conserve bandwidth compared to round robin. For example, here there are one user slot plus 3 unused slots. So instead of having all those slots, we keep one slot with the range 0 to 3 with one active transmitter. So in order to be able to perform our job, we need to distinguish between three states, three cases happening to a slot. So our reception, idle, and collision. Okay, so whenever a collision occurs, we split the slot in half. And then we issue a query for each half. So assuming that we have an initial slot 2649, the base station sends this query and 3 nodes reply to this query. So obviously a collision occurs. So the base station splits the slots in half and issues a new query. So node 31 is the only sensor falling in this range. So it replies with a data message, and since there is no other collision in this branch, the base station moves on to the next branch and issues the next query. So here, both 40 and 48 reply, and again, there is another collision which needs to be resolved. So a new query for each half is issued, and this way we resolve all the collisions in a binary tree-like approach. So the thing is, if in the current slot or in the last slot we have one, in the last round we have one slot 2649, in the next round we will have these 3 slots. So we keep track of the new slots to save the already resolved contention. The slot consolidation approach is the opposite, meaning that if there is an unused idle slot, we remove those slots to save bandwidth. But in order to remove those slots, you have to merge their ranges with a non-ideal adjacent slots. So, for example, suppose we have these 5 slots, and the 3 slots in the middle become idle. So we merge their slots, their ranges into one, split it into a half, and combine each half with its adjacent non-idle slot. And the duty cycle adjustment is used to save energy. Basically, if there is enough number of slots in a round so that the node can go into sleep mode by turning off the transceiver and waking up before its next query, then we do that. But in order to be able to achieve this, we need to know the number of slots. And since the number of slots are changing dynamically, the base station keeps track of this slot count. So if there is a reception, the slot count is unchanged. If the slot's idle, it will be removed, so we reduce the number of slots. And if there is a collision, obviously we split the slots, so the number of slots will be incremented. And so for implementation, there are some embedded constraints. We can't rely on recursion, because if the depth of the recursive call is too high, then we're going to run into a problem. And also, we cannot, for example, our system does not support dynamic memory allocation. So, on the other hand, we cannot use arrays to store the slots because of the cost of shifting. So we emulated linked list slots using an array.
extracted views. So this is the flowchart of base station performed after transmitting each query message. So if the base station detects a collision, it splits the slot. If not, it checks if the slot was idle or not. If it's idle, it increments the idle counter. Otherwise, it resets the idle counter, and at the end of each round, it performs the slot type consolidation. So the idle counter is used to tolerate some degree of packet loss. So if we find an slot to be idle and we remove it as soon as we see a slot is idle, then that means zero tolerance to packet loss. So we can define a threshold and remove only those slots whose idle counter has reached that threshold. BinMAC is one of the most lightweight hybrid protocols ever designed. So the contention resolution is deterministic. This binary tree-like contention resolution is deterministic in the sense that it does not involve any random component. Contrary to many of the existing contention resolution. So we can apply BinMAC to delay-sensitive application because the transmission delay is bounded. And here is the list of BinMAC features that I'm going to skip. You can just the paper. And okay, at the time of submitting the paper, it was all simulation based. So the stuff that I presented for the real implementation was the things that we have done recently. It's an ongoing project, and I'll be writing a new paper with the results on the real world part. So we simulated the TLOS platform and compared BinMAC with CSMA round robin and ZMAC star. So CSMA and round robin represent the best performance under low and high contention respectively. And ZMAC star is a simplified version of ZMAC for star topology. So for implementing ZMAC, we assumed there is no clock drift, so we did not do clock synchronization, and so the network is star topology with 20 sensor nodes and a base station, and we vary the event period to test the system under both high and low contention. And each event requires 10 successful transitions. So here's the throughput diagram. So under low contention, as you can see, all protocols achieve the same throughput because there is not much load, basically, so all protocols can handle this. As the contention goes high, CSMA shows a better performance because of basically low or non control packet overhead. BinMAC and round robin shows a very close performance. ZMAC achieves a little higher throughput, and that's because of lower control packet exchange. But this is the overhead that you have to pay. So you're going to implement this protocol for a very tight ultra compact sensor, so you have to pay price. So in terms of latency,
as you can see under low contention, BMAC performs very close to CSMA, and under high contention, BMAC, CMAC, and round robin are perform almost closely, and the reason for the short delay of the CSMA is that it does not it drops a packet after a number of transmissions while other keep sending onto the packages delivered. In terms of success rate, obviously round robin is always 100%. BMAC is most of the time very close to 100%, but at this point, which is kind of a turning point, so we have a lot of splitting and consolidation at this point, but still it's less than 5%. So we define duty cycle as the radio on time over on plus off time, and as you can see, under low contention, BMAC is closest to CSMA, and under high contention, it's closest to round robin. And in terms of energy efficiency, again, you see the same result. Low contention closest to CSMA, and high contention closest to round robin. And in terms of scalability, so we vary the number of nodes from 10 to 150 nodes, and as you can see, the BMAC and round robin, you see a slight performance degradation, but it's a lot more scalable than the contention-based systems. And here are the results for the real implementation, and this is the same event captured using round robin and BMAC, and as you can see, BMAC was able to capture the event with a lot more resolution. And in conclusion, BMAC is a very lightweight hybrid MAC protocol designed for ultra-compact wireless sensor nodes. It can adapt to the contention level very well, and can adapt larger scale very well. It employs a deterministic contention resolution, which is suited for application with real-time constraints. It does not require plug synchronization, and low carrier sensing on the sensor nodes is required. So thank you for your attention, and if there's any questions, I'll be back.
Question from the audience? I have a quick question. So you mentioned that BMAC is too complex, and I'm actually not too convinced by that, and especially you claim the protocol you have is lightweighted. I wonder, have you, the reason I'm not convinced is most of the time, part of the MAC protocol will be implemented in hardware. So that's why I'm not convinced why your protocol is lighter than like BMAC.
Okay. So it is definitely lighter because, as I said in the beginning, the footprint requirements of EMAC, XMAX, or SCP is at least 18 kilobytes, right? But our sensor nodes has only 4 kilobytes of memory. So it's almost impossible to implement such complex protocols on ECO. For example, our sensor node has like 30 bytes of data buffer. So you cannot add too much code to the sensor node. Okay, but we have been able to implement DMAX on ECO, but definitely we cannot implement any of those. And
so your definition of complex is the storage size. Is that, am I understanding correctly?
yeah, that would be one aspect. Yeah.
We can take this offline.
Sure.
Our next presenter is Sashi Prab. He is currently a research scientist at Polytech Potoc. He graduated from University of Virginia. And he's gonna tell us a different MAC protocol. Instead of Big Mac, now we have BEMMAC. And BEMMAC, an optimistic MAC protocol for reliable communications in body area networks.
How do I make it full screen? So this is joint work with Fernando Roy and Teresa Olivares from University of Castilla-La Mancha in Albacete, Spain, and Stefano Tellina, who is my colleague at Polytechnic of Porto. So by body area network, we mean a bunch of sensors placed on body of some human being, and they take measurements, and this measurement is collected by some coordinator, which could be your smartphone. The data is available to a bunch of service providers. So you can see this opens a lot of possibilities for new kinds of services. Another problem is, like in hospitals these days, rooms more look like physics laboratory than hospitals. There are so many wires. So there is large room for human error, right? So in this cartoon, for example, it says we just set a new record for 7 wires in operation. So basically, one important aspect is to get rid of these wires. Okay. So what is the main problem here? The main problem is, if you want to apply body area networks to healthcare, then reliability is really crucial, because if the system fails, then somebody will have to pay for it with his life, maybe some disabilities. So it's really crucial that the communications are reliable. So what makes the problem more complex is that since these nodes are placed on body of humans, therefore the transmission power has to be kept low. But the low power transmissions are known to be very error prone. Okay, and what makes the problem even more difficult is human body has its own shadowing, which has high attenuation of received signal strength, which I will show you in a minute. So the solution that we propose in this paper is to use opportunistic transmissions whenever RSSI fluctuates. And why that will happen. So let's say we have 2 nodes, a coordinator placed around pocket of somebody, and there is one node at the leg. And let's say this guy is walking. So as he walks, see, sometimes these nodes have line of sight, so RSS will be at its peak, and when the leg is at the back, there is huge shadowing, and the RSSI will be at its low. So in practice, actually, this fluctuation is really not nice, as you can see. I mean, there are fluctuations, but there is high amount of noise. And RSSI is notorious for being noisy. It's nothing new. we did some measurements. So in this measurement, there was a coordinator placed around the pocket of a person, and then there were two nodes, one at leg and another one was at arm. And this is volume plot of the RSSI that we got. And you can see that the fluctuations are of the order of, I mean, in some cases it's a small, so arm is close to the pocket, so you see RSSI has a small fluctuation. This is at leg and it has large fluctuations. So it goes from 2 to 12 dBs, which is significant for low power transmissions. And the other thing to note is that we did this experiment on 3 different platforms. It's Shimmer 2, Mica Z, and Telos P, and you see the trends are similar. So it's not platform dependent. So then here basically what we're trying to do is we try to schedule transmissions when RSSI is likely to be higher than average, because then you have a chance of getting high reliability. That's the basic idea. So we assume some kind of star topology. There is a coordinator and it can talk to all nodes, and all nodes can talk to this coordinator. Some of the nodes are, let's say, on hip, that is not a moving part. Some of the nodes are on your legs or hands that can move. So those nodes that are on your hands or legs, they move and they show some kind of fluctuations in RSSI. The nice thing about human movement is that it's symmetric. So your left hand and right leg will move in synchrony, right? And same for the other, so right hand and left leg. So you get basically a symmetric counterpart, which you say opportune transmission window set 2 and set 1. So basically you need to get opportune transmission window for only one set of nodes, let's say right leg and left hand, and then you can infer about the other set automatically. So the question is, how can we predict these opportune transmission windows? The issues, as I mentioned, are extremely noisy RSSI signals. Okay? And also human movements are not machines. I mean, they're highly irregular. Sometimes people will stop, sometimes their speed becomes faster and slower. So any naive approach is likely to fail. So what we observed is that if you look in the frequency domain, the dominant peak turns out to be corresponding to the walking speed of a human being. So, for example, in this case, the guy is walking on a grass slowly, so you see it's about 0.9 hertz. When he is walking on racetrack, he's walking faster, and you see the dominant peak is around 1.2 or 3 hertz. So the other thing is to find phase, because we need both to predict the peaks of RSSI. So for this we use the idea of passing, very tight band pass filter on the RSSI time series. And this is on the real data. Okay. So this is entire algorithm. I'm going to skip in the interest of time. But basically the idea is that the coordinator, again, there are issues of time synchronization also. So furthermore, since we assume more or less that the coordinator will be more powerful than the nodes, it makes sense to push all the communications to the coordinator. So the coordinator will initiate some kind of RSSI probing mechanism, and the nodes or one of the nodes will be designated receivers, and it will collect the RSSI values and transmit it back to the coordinator, who will do the processing which I explained earlier. So based on this, we have a MAC protocol which we call OneMAC, and we implemented it on top of 802.15.4 protocol, and it works in both beacon and non-beacon in every mode. There are some trade-offs which you can see in the paper. So it works like all 15.4 protocols in 2 phases. There is association phase when nodes associate to the coordinator. So coordinator initiates the association phase with some association beacons, and nodes will reply to these beacons in CSMA mode, so there is possibility of collisions. And then there is a timeout mechanism after which the coordinator sort of determines that it has received all the requests, and then it processes them. Based on that, so it basically it's a pool-based mechanism. So each beacon from the coordinator contains a schedule for all nodes that are associated. And so in this schedule, there is a slot for sending of RSSI time series. And that's why that time series collection is interspersed with data transmission, so it's not a blocking operation. And I mean, we actually will show that we have evaluations in which it works perfectly fine. And after each beacon interval, this scheduling process from the coordinator continues. You can look at the other parameters like beacon order and stuff in the paper. We also implemented, extended this implementation for co-located networks in which there are a bunch of people in one room, so there is possibility of two bonds operating on the same channel, and there will be huge interference. So we solve it in both ways. It's seamless. So there is, in one mode, there is a global coordinator that coordinates which bond will operate on which channel. And the reason we did it is, in some hospitals, it may have some policy to assign certain set of channels to certain bonds. And also it's extendable to other operations, for example, collecting data from these bonds to coordinator and to some other networks. So in this mode, this coordinator basically will assign some channel with some lease time, and after lease expirations, these bonds will request for another assignment, and so on and so forth. And in the distributed coordination mode, there is no global coordinator, and nodes basically decide which channel to operate on among themselves. Here is our implementation. It's obviously open source. Part of it is we implemented on TinyOS. So basically, the sensing part is on TinyOS, and the signal processing part is written on C++, and currently we have it running on laptops, but this obviously can be run on Androids. And you should see there is an alternative available in the market. Xsense sells these systems at 13,000 euros per kit, and each kit has about 6 nodes. And this the system that we implemented, I mean, it has TinyOS and some Android phone, and you can see you can have a system for 300-400 watts. There are some evaluations. So this is single bond evaluation. We measured packet loss. So you see the red curve is for bond, the green curve is IEEE 15.4 without bond MAC. So in the case of bond MAC, we see consistent 0% packet loss until minus 21 dBm. That's because at this power level, the coordinator is not able to receive packets from other nodes. So it cannot decide the OTWs. Here we also we basically compare RSSI, and the thing to note is that the higher bar means lower RSSI, because you see the axis is a negative numbers. So for BondMac, you see consistently higher RSSI for all nodes. These are for 5 nodes that we shown earlier, placed on a human being, and each one is evaluated for different power level. Here we basically try to see if if OTW works, then it makes sense that if you send exactly at the center of OTW, then you should get higher RSSI and higher reliability than if you transmit a bit off the center. And this evaluation basically confirms that. So these first 2 bars correspond to the nodes that are close to the coordinator, and these two, the blue one and the pink one, corresponds to the nodes that are farther from the coordinator. And in the first four sets of bars, they operate in low priority mode, and in the next one they operate in the high priority mode. And you see in the high priority mode, the nodes that are farther from the coordinator have higher RSSI. And also significant, statistically significant higher packet reception rate. These are packet loss rates. Here is evaluation for the distributed body area networks. We have a bunch of people running in the room, and to deal with time synchronization, we have a bunch of sniffers, each operating on separate channels. So we restricted this evaluation to six or seven channels. There were 5 bands, and then there was one interferer, and then there was one global coordinator. Each one required one channel, so we had 7 channels. So we had 7 sniffers here, each sniffing on predetermined channel. And as you can see, the system works perfectly fine. So with the global coordinator, each one is assigned a unique channel, and then at some time we turn on one interferer at channel 23 here, and the band 2, which was operating on that channel, immediately switches to some other channel, which leads to some other band 3 to switch to other channel. Okay, works perfectly fine. Here we break our assumption of one unique channel per band. So there are more bands than channels available. So you see, from about 200 we turn on this interferer. Before that, there are 5 bands and 5 available channels. When we turn on the interferer, there are more bands than available channels, so immediately there is some shuffling. And you see, still a lot of bands are fine because there is no contention. On this channel there is some contention, but when we turn off the interferer, immediately this black, which is band 1, switches back to a unique channel, and all of these bands have unique channel. The convergence time for both coordinated as well as distributed mechanisms was less than 9 seconds for combined, and if you look at the CDF, it's less than 5 seconds for about 99% of the time. So in conclusion, I showed you that shadowing due to human body causes severe attenuation. I presented an RSSI-based algorithm to predict Gaussian transmission windows, and I presented a MAC protocol that uses this idea of opportunistic transmissions and an implementation over IEEE protocol stack. And basically, evaluations confirm that this MAC protocol that I presented provides reliability and also differentiated service.
Very interesting work. I'm wondering how many volunteers you can get to measure body area networks. Any question from the audience? So I have one question. Now, when people talk about body area networks, people talking about implantable medical devices. So I'm wondering whether you ever thought of, let's say there's a pacemaker in human heart, and if you want a pacemaker to join the body area network, will the pacemaker be able to use the same protocol? Basically, will the same protocol work for sensors inside human body?
Yeah, I mean, it works for both. So the idea is that if you have fluctuations, you use this. If you don't have fluctuations, then you schedule them whenever you get a chance. So the pacemaker will not have any fluctuations because it will be a stationary kind of part.
So the fluctuation comes by the movement of human body.
Actually, we are extending it for the case when no movement.
So
do you think that the reliability will ever come to the point that this can be actually used for safety critical applications?
I mean, right now it is showed. I mean, so okay, so I mean there are two things. So I mean, for example, in hospital case, you have these wires running into your body during operation. I think this is not going to happen at that in that phase. But let's say you are recovering, then you can be ambulatory, right? And the risk is not so high. I mean, so I guess in that scenario it's applicable. But still, we need to go much further because this only applies to the nodes on the moving parts. Still, we have to solve the transmissions on the stationary ones. But in other cases, for example, they measure the performance of athletes using these kind of systems. I think for that it's perfectly fine. I mean, you get a small error. The athletes, movement is not hampered by wires.
Not so critical as well.
Yeah, not so critical as well.
So in your experiment, you mentioned there is some interferer you bring in. I wonder how loud they transmit and how wide and what's the frequency
So
range?
I mean, we basically programmed them to transmit the unmodulated carrier on one channel at the highest. I mean, so 0 dB and is the largest power that you can get on those signals. So that was
It's a random signal, it's not like just a tone.
no, it's unmodulated carrier. So yeah, it's continuous noise.
So I wonder, because if it's continuous unmodulated carrier, then using filter, you can filter out that frequency out pretty well.
Yeah.
So,
But here the idea is not to filter it out. Here is to see if that's happening, then you switch channels.
yeah, so I'm just wondering whether any built-in feature in the sensors you're using, they already automatically filter out the interference.
Yeah, but that depends on sensors, right? So not all sensors, especially some kind of sensors that you will have like diabetes, pumps, and those individual things, unreleased
We can take that offline. Okay, so that's it. Speaker again. Our next presenter is, I tried to pronounce your name, excuse me. So Turis Nicolatisi, and he's a professor at University of Pasteur. He also is the director of Sensor Lab. His research area is wireless sensor network, ad hoc mobile computing. Today he's gonna talk to us about his work on radiation awareness in three-dimensional wireless sensor networks.
Okay, so hello, Miha, okay, and I'm going to talk about radiation awareness in wireless networks. This is joint work with two students of mine, and also Victor Kazana from USC, and Rosero Lim from the University of Geneva. So we envision a smart wireless environment composed of both heterogeneous wireless networks like Wi-Fi, Bluetooth, cellular, etc., but also wearable or even implanted wireless devices together with medical equipment. And we would like to investigate the impact of wireless transmissions to creating a high level of radiation in the network. So let me briefly, and a bit roughly so far, define radiation. So we call radiation at the target elementary surface the total amount of electromagnetic quantity in terms of energy or power density this area is exposed to. Even though each device individually may create radiation pool which can be considered rather limited, the additive and correlated superposition of several sources may lead to cumulative radiation whose impact both to humans but also to sensitive nanoscale devices may be at least worth studying and control. And let me note that although there is some research on the impact of mobile phones, mostly on the brain, etc., this seems to be the first study of radiation and its potential impact, particularly the control of radiation in the context of computer science and particularly distributed computing. So the fact is that almost all wireless devices operate in the so-called non-ionizing spectrum. The impact of such frequencies include both thermal and non-thermal effects. So thermal effects have been studied quite a long time, while non-thermal effects have not still attracted the necessary concern by scientists. So let me give also some electromagnetic background. So if the wireless environment is diverse and heterogeneous, then the created electromagnetic radiation pattern is very complex and time and space dependent. Field distributions vary highly with time and space. The on-body devices interact with each other in terms of several parameters like their distance, their relative position and characteristics with respect to radiation, but also human presence tends to affect radiation. So let me give you a graphical example. So this is how the radiation field is looking in the case of a single antenna, on-body antenna. Here we see 4 antennas planted on 2 humans nearby, and we see that in this case the antenna has a rather simple shape, while in the other case the radiation pattern becomes more complicated. So actually, let me make a parenthesis here. So this may give rise to the need of new combinatorial models, new models of interactions, new abstractions, new types of graphs, new types of stochastic processes. But in this very work today, we only focus on capturing radiation in terms of power density, and we only focus on sensor network. Okay? I will come back to that at the future work slide at the end. Okay. We will first define the point radiation and path radiation, evaluate radiation in known network topologies, then define the problem we are going to study in this work, provide several online heuristics and an optimum for this problem, and then conclude with some performance evaluation. So the model basically, we have a Poisson process for data generation. Then we have that the duration of transmissions is captured by an exponential random variable with parameter lambda prime, and TE is the time an event E occurs in the network. So this is the basic definition we're going to need. Other than that, we have a 3D deployment of end sensors, and we denote by this symbol the distance of 2 points in the 3D region. Now, so the radiation at a point during an event E caused by a single sensor V is given by this formula here. So this is capturing environmental conditions. This is the duration of the transmission, and this is the wireless transmission range over the distance. So we see that, first of all, we see that if we are close to the source, radiation is higher, while if we go further away, radiation becomes much smaller. And let me note that here, the impact of the transmission is multiplicative. This is just our choice. I mean, detailed experiments could suggest that this impact should be exponential. But in this very work, we assume a multiplicative impact of duration of transmissions. Then in order to evaluate the total radiation at the point during all events in a certain time interval, we have to sum up overall sensors and overall events occurring in that interval. And finally, in order to evaluate the maximum radiation throughout an interval, we actually discretize and the time interval take the maximum overall created interval. Now, what about path radiation? Let P be a path in the 3D area, and let P T1, T2 be the part of the path that the moving particle traverses from time T1 to T2. Okay? Then in order to evaluate the radiation that the mobile entity absorbs when moving on that path, we have to sum up overall nodes, overall events occurring at that time interval, and then integrate overall path segments, I would say. So we again discretize, and then we integrate overall path segment. And then we approximate this integral by a sum, straight sum. And again, we have a similar definition for maximum radiation within a time interval. Now, as said, we evaluated radiation in two known topologies. So the first one is a well-known random geometric graph. So we drop randomly points in a plane, and we connect 2 points if their distance is less than r, which captures the wireless transmission range. So, through some mathematical analysis, we are able to calculate, to evaluate the expectation of the variance. So basically, we see that the expectation is proportional to the density of the network, so the number of sensors, to the event generation rate, to the duration, so this lambda here, to the wireless transmission range, to the what's that? The duration of the event, and inversely proportional to this factor here, which captures the size of the region. And we see that more or less this here, if this is large, then this cancels out, and we have r square over r sub a square. And then we also have a rather small variance, suggesting a concentration around the mean. Then we also evaluate radiation in the so-called proximity graph. So there, each sensor adapts its range until k neighbors are included in its communication range. Okay? So we actually simulate the previous proof. So we evaluate the so-called effective radius. This is the effective radius, and then we again derive formulas for mean and variance. Then let me come to the minimum radiation path problem. So we have a sensor network at 2 points A and B, and we have an entity, like a human, moving from A to B, and we want to take the path minimizing the total radiation absorbed. Okay? So we're going to provide 4 heuristics. So the first one is the trivial one. So you just move on the line. This is just for comparison purposes. So the first non-trivial heuristic is minimizing greedily radiation. So in each step, we choose within a certain cyclic sector to not deviate too much from the greedy optimal solution. That node which has lowest radiation. Okay? This, unfortunately, can lead to quite long paths. So in order to alleviate this effect, we come up with another algorithm that optimizes the radiation progress trade-off. So here, we take a next position that minimizes the product of the radiation times the proximity to the data to the destination. Okay? And yet another improvement is a trust-based or belief-based approach. So we actually take a weighted sum of the 2 suggestions we want provided by distance-based approach, the other by the trade-off approach, and then we take the weighted sum. There is a weighting factor tau, structure trust. If we end up with a good move, which means that the move leads to low radiation, then we enhance, we improve, we increase tau. In the other case, we decrease it, okay? Reinforcing accordingly the component of the weighted decision. We also provide an offline optimum, so we basically tessellate 3-dimensional region into cubes. So each cube is abstracted by a vertex. There are links between nearby cubes, and then we are running basically a shortest path algorithm with weights, where the weight is the radiation to go between nearby vertices. And then we simulate everything in MATLAB. And this, I will briefly summarize. So this is basically the naive solution. Okay? This is so square is the offline optimum. So we see that in order to minimize radiation, we have to take a rather very long path. The circles here represent the minimum radiation heuristic. So it may be trapped in situations like here and never make it to the end, while this is our trade-off solution, which indeed achieves a good balance between radiation and distance traveled. So this is it. Basically, here we see those basic trends in different topologies. So this is a grid. This is random uniform placement. So this is in case you sample more candidates for next point selection. This shows that initially you get some improvement, but this has a limiting effect. So it doesn't make sense to sample too many potential next move points. Finally, we here we picked the cumulative radiation as a function of time. We do it in order to basically demonstrate that no peaks arise, which means that the maximum radiation is not higher any path segment. Not only the total radiation is low, but also there are no radiation peaks.